Today, we want to look at this thing called the tree, okay? And it's a nice progression from what we've been looking at because we started with this idea that an object can reference another object of the same data type. That idea of a reference, okay, to another object of the same data type allowed us to create the object known as the linked list. Once we had the linked list, we could build from that. So that was our singly linked list. What we actually did in class was something a little more complex, something that referenced both forwards and backwards, known as the doubly linked list. That's the one we actually coded. A little more useful because we were able to use that doubly linked list to create the objects known as the stack and the queue through inheritance, which were also similarly connected objects. We also talked in theory about these lists that could also both singly link back to the beginning instead of linking to null. And this was called a circular list. Actually, it's a circular singular list. And although we didn't program one, in theory, we could have also programmed one that's doubly linked, and the end node goes back to the beginning node, and the beginning node goes to the end node. And this is also a circular list, but it's a circular doubly linked list. So that was all the kind of theory we had at this point. But in all these situations, even the stack and the queue, these are all linear type creations. They all follow a straight line. Now the stack, you could argue, goes up and down, but it's still a line, okay? What I'm going to propose today is a similar structure. But this node, okay, is also going to have two references. So it's going to hold data, but instead of thinking of it as linking forwards and back, we're going to think of it as linking out two directions this way. And the beauty of this object is, if this is what we're going to create, just group it and shrink it. Then this object can be created in multiple places, like this. And this creates the so-called tree object, okay? So the idea with this object, the reason it's called a tree is the way you imagine it is that you've got the ground, and the tree usually grows up from here and out and branches out like that. That's the way we visualize a tree. Mika, don't criticize my art skills. So that's the idea, but we're going to take this object and flip it around, okay? That's the way you want to visualize the tree object, okay? Drawn more simply, it has a node that connects to nodes this way, like that. Okay, so this is the tree object. It makes use of a lot of stuff that we've already been doing, but a lot of the inner logic that we're going to deal with this thing changes, okay? As well, we got to change up some of the terminology we use with this thing. These will still be called nodes. That still makes sense to call those nodes. But we're going to come up with names for the connections, okay? The connection between each node can essentially be called a branch, right? If we use the tree analogy. If we were using a math analogy, you could also call that an edge, okay? It's an edge connecting it. But I like the term branch. It kind of makes more sense in the tree analogy. As well, we also might not just call them nodes, but we can be more specific about the node, okay? Just like in the example on the previous thing, if I turn this back around to be an actual tree, Okay? The part where the tree hits the ground is often given a name. Actually, more accurately, it's sort of the part that's under the ground. We usually call that the root of the tree. Okay? And at most trees, at the very end of a branch, okay? So yes, this is a branch. And at the very end of a tree, we usually have a thing called a leaf, right? So the leaves are at the ends of the trees and the root is at the beginning. So in the realm of computer science, we've used that terminology. So this node right here is called a leaf node, okay? Because it's at the end of the tree. This node right here is called the root node because it lies at the beginning of the tree. That's the entry point into the tree. The tree starts here, it branches out, eventually reaching a leaf node, okay? Now similarly, I can have more branching occurring in different places, okay? And it could branch out from there, but that's some of the terminology we want to use. So that we're going to have these words leaf, root, node, of course, branch. Okay, so those are some of the terms you're going to hear me say in this unit. Okay? As well, the neat thing about trees is they kind of maintain the same properties all the way through the tree. So at this point in here, I can just take one portion of the tree, and I'm going to call that a sub-tree. And for that particular little sub-tree, it also has its own roots and leaves. So each inner part of the tree has the same properties as the whole tree. Now, if you think about that, what that can lead to is a whole different kind of logic than it's related to when we work in a line. What this can relate to is the fact that trees are going to use recursion. They can use recursion to up the logic here because each sort of portion of the tree is true for the whole tree. Okay, so there's some of the terms we're going to need. Now, for any particular node, any node, just somewhere in the middle of the tree, it could have something going in it, and it could have some things going out of it. Okay, right? Like depending on where that node is on the tree. So it could have some branches going in. And it could have some branches going out. Okay? In tree studies, we do this by measuring what's called the in degree of a particular node and the out degree of a particular node. So the number of nodes going in this case it's 3, is its in degree. The number of nodes, or sorry, the number of branches coming out is its out degree, in this case 3. So now if I go back to the previous tree and I pick any particular node, this node, for example, right here, it has an in degree of 1 going in, and an out degree of 1. What's true of every leaf node? Every leaf node, you know one of those values, no matter what. 0 what? Out degree, yeah. It'll have a 0 out degree, no matter what. So leaf nodes will always have a 0 out degree. We also know something about the root node. What's true of the root node? It'll always have an in degree of 0. Root nodes will always have a 0 in degree. But for any other node, it could be different, right? In this case, I've drawn what's called a binary tree because it all branches into 2s. But that's not the only kind of tree you can create. But in general, every root node will have a 0 in degree and every leaf node will have a 0 out degree. And that's actually how you can tell that those are the nodes. Okay? So Another term that you may hear me use is the term degree, in terms of in or out degree. Okay. Let me show you a little bit of what I have for the presentation for this. Okay. So you're going to see again some of this terminology, and it's important to grasp some of these terms as we start programming the tree. Because if you get the terms down, it's easier to talk about the tree in its sort of context. All right, come on. Come on, PowerPoint, you can do this. Okay, so some of these definitions are a little mathematical. Just sorry for everybody, I'm going to dim the lights here. So although we've been looking at linear ADT structures, the tree is a non-linear structure, okay? It's a hierarchical structure. It's a connection. In graph theory, the definition of a tree is a linked set of nodes that has no looping within it. Don't worry about graph theory. That's a little beyond the IB course, but we may even look at that this year. So in your IB curriculum, the type of tree you need to know is known as the binary tree. We will look in theory at some more complex trees beyond the binary tree, but that's the one you need to know. And I'll show you again, we looked a little bit at the curriculum last week. So trees represent relationships. So some of the other terms you're going to hear is parent and child, okay? So for example, A is the parent of node B and C. That's pretty simple. Node D is the child of node B, right? D is the child of B. Now we could extend that terminology further. We could describe B and C as siblings on this tree. We could use the term grandparents if we wanted to, or great-grandparents, but that gets a little convoluted. We don't need to necessarily get that detailed in our description of things. Just that we know that every tree has at least one parent or one root node, okay? And as well, every tree will have at least one or zero leaf nodes, okay? By the way, the root node can be a leaf node. A tree could have a value of 1, right? It could have a value of 0. Okay. So nodes that have no children are known as leaf nodes, as we can see here. So D, E, and C are all leaf nodes, okay? A is the ancestor of D, E, C, and B, okay? In degree and out degree, as I've already explained to you, are the number of nodes going, or sorry, the number of branches going in or the number of branches going out. As well, subtrees are portions of larger trees, and subtrees contain the same properties as the tree itself, okay? All right, so now let's switch to binary trees specifically. A binary tree is defined specifically as a tree that has either a single node, right, just one root, and a collection of subtrees within it. So the tree could be empty, or it could be partitioned into 3 distinctive subtrees. So the root, and the left subtree, and the right subtree, okay? Now let me kind of stop for a second and explain what I mean by that, okay? So let me redraw a binary tree, okay? So the basic value is you could have a binary tree. So now we're specifically talking about binary. So a tree could be empty. There could be no nodes. A binary tree could have 1 node. At that point, it would just be a root. That's it. But a tree could also be a collection of a root node and a left subtree, okay, or a root node and a left subtree and a right subtree. And that's it. That's the definition of a binary tree. Now keep in mind that each subtree holds the same definition. So for this subtree, it's either just a root, or a root with a left, or a root with a right. So a binary tree can be empty, just a root, and a left subtree, and a root, and a right subtree, or a root, and a left subtree, and a right subtree. So really that's the 5 different ways we can have a tree, right? So let me show you an example of all 5 of these. So there's the empty tree. That was easy to draw. There's just a root. There's a root and just a left subtree. Here's a root and just a right subtree. Okay? That's a whole subtree within it. Or a root and a left subtree and a right subtree. Okay? Those are the different sort of possible trees. Okay? So just an empty one. Okay? So 1, 2, 3, 4, 5. So this is type 1, 2, 3, 4. Sorry, that's 5 and 4. Okay? And keep in mind, when I say subtree, it's the same definition. So here, this is a root, and this one is a root and a subtree. This one is a root and a subtree, and this subtree right here maintains the same definition. So it's a root and a left and a right. So this is 4 plus 5 as the subtree. Okay, I think I'm getting a little confusing here for some of you, but your silence is worrying me. Okay, so that's the definition of a tree. Okay? It's defined as a full binary tree if every node is present at every level. So let me show you some examples. That's a full binary tree. It has 1 level, 1 node. That's a full binary tree. 2 levels, 3 nodes. Every node is present. That's a full binary tree. If, for example, this one was gone, that one right there was gone, it would no longer be a full tree. It would be a partial tree. Okay? This is a full tree. 4 levels, 15 nodes. Now, let's see how mathematical you guys are. Can you figure out a relationship between the level and the number of nodes? And I'm going to warn you, it's not an easy formula. So at 1 level, we get 1 node. 2 levels, 3 nodes. 3 levels, 7 nodes. So what's the relationship between 3 and 7, 4 and 15, etc.? Or x and y? It's hard. Okay, I'll give it to you. It's 2 to the L minus 1. 2 to the level minus 1. Okay, that's how you can determine the number of nodes. But it's related. It is a linear relationship. It is well, not linear, but it is a relationship that is mathematical. Okay? So that's the theory. So now we're going to program this thing. We're going to write code to do this. So if we go way back to here, when I first introduced it to you, this idea of a node, because it's all based on the node. So we're going to have a node that holds data, as I said before, and let's draw it out this way. Rather than call those next and previous, we're going to use better words for these. We're going to call this left and right. Okay? So our node will contain data, and it'll connect to the left tree and the right tree. Okay? What we can't then use is we can't use the node class that we've been working on. Because if you take a look at the node class within here, it uses the words next and previous. And that's not going to cut it. So we will have to build a second node class. So although we're almost out of time today, let's get started with that. And we're going to continue this within our big example. So we're going to put a node class inside our collections package called TreeNode. So we'll just make it a little more specific. So we're going to make a new Java file, a new Java class called TreeNode inside of our collections package. Okay? Now, the question I want to ask you guys is, how complicated do you want this class to be? In other words, we could make this generics, like we did with the linked list example. Or, if we want to shorten up the code and shorten up these examples, We could make this just a simpler tree of, say, for example, just integers. So how many of you would like to do it simple, or how many are ready to just go for it at the level of generics? Generics? Where it's going to be hard, most of it is not going to be that hard. Where it's going to be hard is, what you're going to have to do with trees is you have to, unlike just regular nodes where you checked if two things were equal, with trees we have to check to see if one thing is less than or greater than. And how do we do that with things like strings? How do we check if they're less than or greater than? Is cat less than dog, etc.? So, and how do we do that with generic objects? How do we check to see if they're less than or greater than? So we can do that, we can code that in, but it is going to be a little bit tricky to do that, and it may not always work in all cases, okay? But I'm with you. Let's make this a generic tree node. So the data, public T data, will be generic, and we will have a connection to the left. Whoa. And the right. This is different than our other node class, which connected to previous and next. We are now connecting to left and right. Okay, and we're going to stop there for today. Everybody, let's continue our look at trees. So yesterday, we started with this idea that the tree is an extension of these advanced, okay, or this is the idea of the ADT, okay? Sometimes it's said it's the advanced data type. More accurately, it's the abstract data types. Abstract being that these things are not locked in like variables and arrays, that these things grow and shrink and are dynamic with the program, okay? So these are abstract data types. So we're extending on, like we did the linked list, we kind of went through different versions of that, then the stack and the queue, and now we're kind of going to the next level with the tree object, that the tree object is not linear, but instead follows a sort of branching structure. Just like a tree itself, it branches out. And we talked a little bit about some of the terminology there, like all these little terms that we came up with. So there was stuff that we talked about, like that trees use nodes, but it's not going to be the same node as the linked list because it's not going to go to back and front. It's going to go to left and right, okay? That there are branches, okay? That there are parents and children. So there's like this parent-child relationship happening there, right? And that's pretty simple to see in sort of a general idea. That we had the idea of in degree and out degree. And that's specific to each node, that it has a certain number of inputs and outputs. What else? We talked about a lot of that stuff, right? We talked about that trees are based on subtrees that maintain the same property as the tree itself, that a subtree is also part of the same sort of general idea, okay? You can see here we did kind of get the general idea of this down, okay? We also talked about the specific types of nodes, that there are leaf nodes and there are root nodes in a tree. Well, there's actually a root node 1, okay? There isn't really a name given for nodes in the middle, okay? They just are generally called nodes. But like you can see that that's a leaf node, right? That one's a leaf node, and that one is the root node, right? Etc. So we got the terms down. And we started programming with generics. However, for this to work, especially when we look at the tree that we're going to be required to learn, which is the binary tree. Binary, of course, means 2. That the binary tree holds certain properties. Okay? So what I want you to do right now is give me a list of, say, 5 or 6 random numbers. Please don't put them in order. 42. Come on. 16, 7, 6, 972. One more. Make it negative. No, don't. One more, quick. 53. Okay? We'll make the 6 negative, just for fun. Okay. Now let's imagine that's the order in which these numbers came to us. When you build a binary tree, it will build it based on the order it gets them, but it builds them in a very specific way, okay? So as you would imagine, the 42 is built as the root, okay? It's the first node, so it's going to be the root. Now the 16 comes to us. Where do we put it? We can put it on the left, or we can put it on the right. It doesn't matter. Now you'd think it's random, or maybe we always go left to right, but we don't. With a binary tree, the way it works is, if the next number I'm getting is less than this number, then it goes to the left. And 16 is less than 42. So it goes there. Now I go to the next number, 7. But I always start at the root. So is 7 less than 42? So it's going to go to the left. But it doesn't replace this node. It does the same thing. Is 7 less than 16? Yes. So it goes to the left of 16. Now I get negative 6. Negative 6 is less than this, and less than this. So negative 6 goes here. Now I get 972. Starting at the root, 972 is greater. So it goes there. Then I get 53. Well, 53 is greater than 42, but it's less than that. So this is the shape of the tree it would draw. Mika. What if you get another 42? Generally with trees, they sometimes don't allow equals. That's one thing you can code. Or it will generally consider it either less than or greater than. As a programmer, that's up to you. Generally, I find most programmers put it as less than or equal to. So the 42 would have gone that way. That's an excellent question. But here's a neat point. What if these same numbers came in a different order, right? So I'm just going to take the tree we drew and shrink it down a little bit. So just shrink it off to the corner there. Now, can I actually adjust these numbers? Oh, I wish I could. Let me just break this apart. Okay. 7, 6. Okay. So now I'm going to reorder these. I'll just randomly just mix them up. What happened there? Okay, so. Okay, so let's say they came to us in this order. Okay? What would the tree look like? Okay, so I'm just going to pause my recording for a sec. So this is not that difficult, I hope, especially if you practice it a couple times, to understand that trees will be built, binary trees, based on this basic structure. But for this to work, we have to compare using less than or greater than. And with integers, that's easy. But as we were just talking about, with other data types, this is a little more challenging. So I don't want you guys to code this, but I just want you to watch what I've set up here. I've set up a little demo in main here. And the demo goes like this. I'm going to output what x is. I'm going to output what y is. And if x is greater than y, I will output that. Now I'm doing this using something called the compare to method. Okay? Now, we've talked about how equals is built into every single Java object, and that's true. And I also said when you guys write your own Java objects, it's good to override the equals method so that you can determine what's there. Compare to is not in every single Java class, but it's in a lot of them. Because we don't always need to compare two things to see if they're greater or less than. But sometimes we do. And the one that you may have encountered before is the string. So I'm going to make a string A equal to a new string, which I don't have to do. I could just say equals, but I'm going to do it this way using the string constructor. Okay? And I'm going to make string A, A. And I'm going to make string B, B. So which would you imagine is greater than the other before I run the code? Do you think, and actually, sorry, I'm not going to make this A and B. I'm going to make them X and Y. Okay? So which do you think is greater, X or Y? Y. Okay, so you think that B is greater than A. That makes sense. So this code should run. It'll display what x is, and x will be a. It'll display what y is b. And then it'll use the compare to method to check them. Okay? So let me run this. Now, compare to method is a little bit of a weird method to use. We'll look at the sort of details of it in a second. But let me just run this to confirm our suspicions. And it says that x is greater than y. Or sorry, x is less than y. Which is true then, so y is the bigger one. So a is less than b. That makes sense, that a is less than b. And it's outputted that, so it's outputted this if statement right here. It's compared x to y. Now the way compare to works, you can see it kind of in action right here, is it returns an integer. So the compare to method returns back a number. If that number is less than 0, then this thing is less than that thing. If the number is greater than 0, as you can see up in this one, then that one is greater than that one. And if it equals 0, then they're equal. So actually you can use compare to also check if two things are equal. Okay? So, and you can see that in my output here. So let me show you what I mean by that. I'm going to make them equal right now. So I'm going to make them both equal. So there's a and a. X and y are both equal at this point. And when I run it, it says that x equals y. They are equal. Okay? Now I could have used dot equals there. I could have said if x dot equals y, and it would have also registered as true. Okay? Now, the neat thing about compare to is it's built into lots of classes. So I could make this string into an integer. Okay? So that's an integer. That's an integer. Okay? I'll make this one 10 and this one 20. And I run it. Works the same way. I can make this into a double. So I make x a double, y a double. I'll make it 1.0 and 2.0. Run it. Works just fine. So compare to is built into those classes. I could even go with Boolean if I want. Okay? Again, I'm using classes here, not primitive data types. With primitive data types, I wouldn't need compare to. I would just use the little less than and greater than sign. So I'll make this one true, and this one false. By the way, which way do you think this is going to go? Do you think true is greater than false? Whoops. So it says x is greater than y. So yes, so true is greater than false. Yes. Yeah, good call. Now, I can also do this with my own class. Okay? So I actually did that. I made a quick sample class. I didn't want you guys to code this in. It's extremely simple. This is called sample class. All it has is one piece of data. I just happened to make it a string. So I built that into the constructor. When you construct the simple class, just pass it a string. I also overrode the toString method so that it can output itself. But then I also overrode the compare to method, which isn't necessarily overriding anything, because compare to isn't necessarily built into everything. But what I do here is I've defined how you compare two sample classes. And for this, all I did was compare the data, right? But let's say this class was more complex. Let's say it was a class of your construction, and it had in it not just one string, but it had a couple integers. Like maybe it was a class that you had that was like, say you were making a game, and this was your character class. And it had strength and lives and mana, is that a thing? Mana, right? So you got all this stuff in there. So when you compare two characters, you might have to compare all those things. But then you could still return whether one character is greater than another, right? You come up with what the comparison is. But if I do this, sample class, it should still work because I've overridden the compare to method. So now I'm going to make a sample class x and a sample class y. Whoops. And it just so happens to take a string. So I'll put an a in there. and a B in there. And it'll also work because I've overridden the compare to method. Okay? So I brought this all up for a reason. We are going to need to do this in our node class because of the fact that we're using generics. Okay? So, all is well. I've proven my point, I hope. Whoops. So now, back to our tree node class. We know something that's going to happen is that we will be overriding the integer return method known as compare to. Whoops. And compare to will take another tree node as a parameter. Let's call it, I don't know, the target. No, sorry, the source. This is the source that I'm comparing it to. Okay? And I will have to write that code, what that is. Okay? Now, luckily, it's based on data, right? Whatever data is. But for now, let's just return 0. We'll get to that in a minute. Okay? But we know that's going to need to be a part of our code. That when I compare two objects, I'm going to need to make that happen. Okay? One tree node has to compare to another. It is. Yeah, it is generic. So we don't know how to compare them. Well, we'll compare them based on the data. Right? So you're right. It is based on data. So like we'll be doing something like this. Data dot compare to. The problem is compare to is not necessarily a part of the data class because we don't know what the data is. So it'd be like that, source dot data. Okay? But here you can see it's going to give us an error. It says it can't find compare to. So we got a bit of a problem there. So we have a problem that we're going to need to resolve. Like I said, it's not going to be easy, but we will find a way to do that. So I'm not going to go into all the details of that today. For now, let's just return 0. Okay? All right, and this relates back to, again, that idea of should we do a deep comparison or a shallow comparison, but we'll get there. Okay, so let's do some of the easier stuff now. We've got to build a constructor for this class. Okay? Now let's leave the default constructor out for a minute. Default's always going to be one of the easier ones to write. Let's write one of the harder ones. Let's write a tree node that takes t data, tree node left, and tree node right. So let's write that constructor to start. Actually, that's not that hard, is it? I just say this dot data equals data. And this dot left equals left. This dot right equals right. We've done that before. Man, something's going wrong with my copy paste today. Okay, so pretty simple code. Now, the reason why I would suggest you write this constructor first is it's going to make our life easier when we write our second constructor for this. And I think you guys will know why if you can sort of plot this out. So the second constructor would be public tree node with just t data. So just like something like this. Now the question is, what do I write for the code for this? I could put the same 3 lines. I could say this dot data equals data, but then I'd have to say this dot left equals null, and this dot right equals null. Or is there another way we can do this? Right. Remember we did this in the previous linked list example? We can just call this same constructor back here. Saves us a little bit of work. Okay? And now let's write the default constructor. The default constructor would be just same idea, no parameter, and I just put a null right there. So that's why I might suggest when you're going to write overloaded constructors, start with the big one first And then you can simplify these other constructors down afterwards. It's just a little less work for you when you do it that way. Okay? So now we have 3 ways we can construct a tree node. Now we could make a 4th way that uses only 1, but I don't think that would be useful, to be honest with you. Because is it the left or the right, and it's just, So we either make it blank, we make it just with data. So for example, this would be a leaf node, right? A leaf node would be constructed with data and then 2 pointers to null. Or just the root node when we first start. Okay? This one could be a node inside the tree that is actually connected to other things. And then this one, I don't even know if we need that one. I don't know if we even need a default constructor here. I think that's possible that we don't. Okay? Now, we have one more method to write in our tree node class. Well, we have to do compare to. We'll get to that in a minute. Okay? But the one that we have to write, believe it or not, is we're going to write an insert method. Public void insert t data. Now this seems weird. Why would the insert method be inside the node class? And not like what we're going to build is a tree class that will use the node class. But again, the reason is because every subtree holds the same properties as the main tree. So the node itself has to know how to insert from itself. And think about that from what you guys just did. You inserted from this node, and then when you were here, you inserted from this node, right? When Jack was doing this, he went, okay, 16 goes here. Then when he got to 42, he went, okay, it goes inserts from here, and then it inserts from here. He was doing that instinctively. But that's what's happening is you are inserting from the node itself, not from the tree. Well, from the tree as well, but okay. So here's how it works. Okay, the code is simple, but it takes a little bit of thought to get through it. If data, that's the parameter, okay, dot compare to, okay, this dot data, okay. So here's where I'm comparing, and if it is less than 0. So what I'm saying right here on this line of code is I'm saying, is this data, right there, is that data less than the data inside me, right? So I have that parameter, I have that property called data up top there in the defined code. I've also passed it a parameter called data, and I'm checking the two. I'm comparing them, right? I'm comparing this one to that one. And I'm asking, are they less than one another? Okay? So here again, we're running into that problem. At this point, data is generic. Because it's generic, it doesn't know if it has the compare to built into it or not. It doesn't know that it does. So we're going to need to resolve that. So for now, we're going to leave that error. Okay? We're going to leave it just based on the logic that this will work once we resolve that. And this if will obviously have an else if that goes with it that will be essentially the same thing. But I'll say if it's greater than 0. And actually, why don't we say greater than or equal to? So we'll get that out of the way. So if it's greater than or equal to, then I do something else. And this is the exact thing that Jack did when he plotted those nodes. He started at 53 and he said, okay, is 16 less than this node or greater than this node? That's what he was doing. And so as a result, that's what we're trying to code right here. We're trying to code a comparison between the parameter and this. Okay? We're comparing them. Okay, so what happens is, now I would know at this point that I place, and you don't have to put this comment in, but I'm just going to put it in. Place the parameter, okay, into, if it's less than this, right? In other words, if 16 is less than 53, into a left node. It's actually a new left node from the current node, which is this node. That's what I need to do. Think about that, okay? So let's say that the node I'm currently in, say this node that we're constructing, is a 20, okay? So that's what's held inside the field data. Let's say I just passed it inside this parameter, the number 15. So what it does is it compares 15 to 20. And yes, 15 is less than 20. So what it says we're going to be doing is we're going to be constructing a new node to the left of our current node with the 15 in it. That's what it said we should do. And that's exactly right. And similarly down here, in this section, we'll just place it to the right of our current node. Okay, you can grasp that a little bit, I hope. Your silence worries me. All right, so here's how the code goes. I'm going to erase my comment now. Okay? If this dot left equals null, this is an important check to make. I know I'm going to be putting it to the left, but I better check. And that's what Jack did, by the way. Jack did it right here. Not at 16, but let's say when he got to 42. He started here, he goes, 42 less than this? Yes. So he didn't put it there. He first checked to see, is that thing a null? Then he went, is 16 greater, or is 42 greater than 16? Yes. He checked if that spot was open before he built the node there. Right? The check to see if it's null is the check to see, is this an empty spot? If it is an empty spot, this dot left equals a new node, pardon me, a new tree node, and I can use my constructor and place the data inside of it. I can already just use that constructor. So if the left is null, build me a new tree node off the left side of me. Right? This is me, right? Now, here's where it gets weird. With the else statement. What the else statement means is, okay, so I got 42, right? 42 is less than 53. Is this thing a null? No. So because it's not a null, what am I going to do with that 42? Well, here's where the code gets cool. What I do is I say this dot left dot insert the data. What is that I just wrote? Anyone can give a name to what that is? It's recursion, right. Insert is calling insert. So it's now recursively calling it off the left side. So it's going to use that left node in a recursion to place itself after itself. Cool, recursion, okay? By the way, all this if statement will also go in the down here. The only difference is, down here, change these to right. Okay? That's right, right, and right. Now I'm just going to take out a couple brackets just to save space. You do not have to. I'm just doing that because I can zoom in a little bit more. Oops, forgot one. Yeah. Okay. Now we still haven't resolved this compare to thing. Okay? We're going to get to that. We won't get to it today. But we've got a way to resolve that. Because we're using generics, this gets a little more complicated. So we're going to have to jack it up a notch. But the logic is solid, right? We're comparing one to the other, and we'll do this. And by the way, this is probably the trickiest code we're going to write in the tree class at this point. Yes? We're going to go to the right, yeah. Now, it doesn't matter. We could put the equal sign on either one of those. It honestly doesn't matter. Just you need to resolve that as a programmer. Okay, so we'll pick up on this tomorrow. This is cool stuff. So we think about this idea that when you insert a value into the tree, it has to decide whether it's less than or greater than. Now, because our class is generic, the object that it's going to become, we don't know what it is. Now, in the case of things like class integer, class string, some of the big classes that we know about, those would be fine because those have built into them something called the compare to method. And compare to essentially does check if things are less than or greater than. And that applies for a lot of classes, but unfortunately not all of them. Not every class uses compare to. Okay? Unlike, say, equals, which we know is built into every single class, compare to is not. And so as a result, we're getting an error in our code because it's saying this generic, I don't know if it will have compare to built into it. So what we essentially need to do is we need to enforce, like law enforcement, that compare to must be a, whatever class I'm going to use as a generic, it must use compare to. Okay, so to do this, we're going to make use of a couple concepts here. So I've prepared a slide for this, thing for this. Since we're using generics and we want to enforce something, we're going to be using essentially these couple things. We're going to be using what's called an abstract and an interface, and specifically something called the comparable interface. And if we just go all the way down to the end here, what does comparable mean? It means to compare things, right? Which is exactly the problem we were running into, okay? So essentially, this is again a crash course. We talked, some of you may remember that last year in grade 11, at the one last big gaming example I did optionally in class, I talked about abstract classes. What an abstract class is, it's a class that cannot be instantiated. So it can only be a class, you can't make an object of those classes. So then you're thinking, well, what good is that? Why would I make a class that I could never instantiate? Well, you use it for inheritance. So it becomes the parent class of other classes, right? So you can have an abstract class. Oh, there's abstract class. And things can inherit, you can have classes that inherit from it, even though you can't instantiate it itself, okay? In the gaming example last year, we made a class called the game object class, and you never could make a game object. But we then made classes like Pac-Man, which inherited from the game object class, and then you could make a Pac-Man. So that's what an abstract class is. An abstract class, is a class that you cannot instantiate. There's also, by the way, abstract methods. Abstract methods are essentially methods that have no body to them. So they're essentially just stubs. They're a little method that has no body in it whatsoever. So that, strangely, if you write an abstract method, it looks like something like this. Public, void, let's call it foo, and it takes a parameter int x, and then that's it. You put the semicolon right there. That's what's called an abstract method. So you're thinking, well, what's the point of that? Why would I have an abstract method? Well, same idea. If you have an abstract method in an abstract class, when you inherit it, then you override it and put content into it. So it's kind of like a template for what's going on. If you extend that to the next level, that's essentially what an interface is. Okay? An interface is an abstract class that has to have abstract methods within it. So you can make abstract classes, but they're essentially like other classes other than you can't instantiate them. So they can have full methods, they can have abstract methods, they can have data members. But taking it to the next level, an interface is an abstract class, but it only contains abstract method. So it can't have things like constructors in it and stuff like that. So what's the purpose of that? Why would I need a class that I'm never going to instantiate that has completely empty methods in it? Well, the other thing what an interface does is it's also being used for inheritance, right? So if this class up here, the game object, is not only abstract, but an interface, what it might do is when I inherit from it to create a Pac-Man object, it will not only inherit from this, but it will force. So if I have, say, an abstract method in there, it'll force me to override it. I must override it. It creates a sort of, you must do this stuff. And that is exactly, whoops, what we wanted. Come on, stupid thing. Right here. We want to enforce that when I create this class, it makes you have to have that method in there. So this one won't be a problem because that method's already in there, that's already in there. But let's say we make our own class called like the creature class. And we want to use it in our tree. Well, it'll force us to write a compare-to method in there, okay? And that's kind of what we wanted anyways. We wanted that to happen. So the simple fix for this then is go to the top of your tree node class. Okay, so we're up at the top. And right here in the generic, you put this. Extends comparable T. Okay, so let me zoom in on that. So it's kind of weird syntax there. So what's happening is the generic is extending something called comparable. Comparable is an interface. It's not our interface. Somebody else made it. But what comparable makes sure happens is that any class that's going to be used with the tree node has to enforce comparable. It enforces the rules that comparable has set forward. Now, I'm just going to read right from the Java documentation of what it says about comparable. I'm just going to, I actually brought this. This is right from Oracle, right from the people who made this comparable interface. This interface imposes a total ordering on the objects of each class that implements it. The ordering is referred to as the class's natural ordering, and the class's compare-to method is referred to as its natural comparison method. Okay? Cool. So it's basically exactly what we're looking for. That this comparable interface, and by the way, and again, I wish I had more time, that's how you create an interface. Instead of the word class, you put the word interface, and then it becomes an interface. If we had more time, I'd love to show you guys some more sort of concrete examples of this, but you'll notice now that by doing that, we don't have any errors anymore. We've fixed our errors. Compare to is now done. It's fixed. So we got a little bit of time before the bell. Why don't we write a toString method for our tree node class? Public string toString. So how do we output a tree node? Well, why don't we do something like this? String text equals the word data equals plus data dot toString. Come on, there we go. But a tree node could have children, okay? So the text plus equals this dot left dot toString. And actually, why don't we put the words left on there, equals left toString, and I'm trying to beat the buzzer here, but right equals this dot right toString. So basically what I'm saying is when you output a node, output its data and output what the left subtree of this node is and the right subtree of this node is. So this is going to be recursive, okay? So I know you guys were just sort of, let me just punch that in. Let me just see what this would do. So if I made a tree node, okay, I know you guys won't have a chance to follow this, but a tree node of type string called x equals a new tree node of type string. And let's put some value in it. So it'll be the letter A. I'll make two more, x, y, and z. And this will be a B and a C. And then I'll say x dot left equals y, and x dot right equals z. And then I'll output x. Okay? So let's imagine what this is going to draw. We've made a node called x that contains the letter A. That's x. Left side is y, right side is z. Let me quickly run the code, see what happens if it actually works. Work! Work, damn you! Have a good day, everybody. Remember, tomorrow, you're welcome to come first period to do your survey, but if you come during your spare, according to the office, that's okay. It's no, it's, oh, of course it's compiling slow. Crashed. We will fix it tomorrow. So we are out of time today. So last time we were working on this tree node class, we really kind of got it in a good space here. But let me just double check to make sure what I have matches what you have. I put in some comments, but what's key to this thing is the tree node is generic data type, so it's a generic. But the tree node extends, this is by the way what I was just talking about with the grade 11s. So it uses inheritance to extend something called comparable. Comparable is an abstract class. Remember, abstract classes mean they are classes that cannot be instantiated. Which means, since you can't create an instance of the class, you can only use it for inheritance. Okay? But as well, this is not just an abstract class, but it's an abstract interface. And an interface is an abstract class, but the interface means that it cannot be instantiated and it has empty methods. Right? So within the interface it has these empty methods that have no content, but those empty methods must, and that's the enforcement, must be overridden. So you must override the methods within the interface of the abstract class comparable. So what that does is it forces our class called TreeNode class to override the compare to method, because that's the method we're looking for. It's all based on the fact that we want compare to has to be a method within this class. Well, specifically, it has to be a method within the class data that the tree node uses. So whatever data we give this node, it has to have a compare to method within it. That's enforced by the abstract comparable interface. Yes? Well, because it's not the tree node class that's extending it. It's the data type T that's extending it, right? It's tricky. Like if these brackets weren't there, then you're right. Then that's what it would implement it. That's right. Okay, but again, none of that's in the IB content, so you don't got to worry about it. Okay, so then we had a constructor, the tree node constructor. We had another couple constructors. We used some fancy this keywords so that it shortened up our code. And the last method that we needed was the insert method. Now it's the insert method that uses compare to, right there. So that's where it became crucial, that whatever the data we were comparing had built into it a compare to method to allow us to check the things that are less than or greater than or equal to. That was crucial because based on that comparison, less than or greater than, we can insert the data to either the left or the right of wherever we are. So whatever node we're at, I either insert to the left or insert to the right. And this is also done recursively. Recursive call there and recursive call there from the left side or from the right side. Okay, we'll come back to this method because this is actually the key to the logic of the binary tree here, is that that is occurring. Okay, does everybody got all that? All right, so now we're going to add a Java class called the tree class. Okay, so this will be our tree. And it's going to go into the collections package. Okay, so the tree class. Well, for the tree class to work on the tree node, it's going to need to do the same extension of comparable. So I'm just going to steal that piece of code right there and put it in the tree class as well, because it will also use generics. So the tree also extends comparable. Well, specifically, the thing that tree uses extends comparable, okay? Because it uses a tree node. So there's a private tree node of data type T. But with the tree object, it only needs one entry point. Now, if this was a linked list, we would use a node called front and a node called back if we wanted a good doubly linked list. We don't need that. We could have just had one entry point. But a tree really only does have one entry point, and it's called the root. So we enter the tree from the root. Okay, so that's easy. Let's write our constructor. Public tree, the root equals null. That was easy enough. Now, in order for the tree to work, we've got to put stuff into the tree. We've got to insert into the tree. So we're also going to need to write a public void insert tData method. Oops. So how do we insert data? This is actually very simple at this level now. There are two scenarios for inserting data. The first scenario is, what if it's an empty tree? Well, how would I know that? How would I know the tree's empty? Yeah, so if the root equals null, then the root equals a new tree node with the data in it. So that's how I insert it if it's an empty tree. The root just becomes a brand new tree node. Otherwise, else, it's very simple. I just go to the root and I insert the data. And it's done recursively at that point. And that's it. That's all I need to do to insert a piece of data into this tree. Okay, let me try to diagram this for you. Well, hang on. Let's put it to the test. Let's go to wherever our main is. I'm not sure, it's our main class is out there somewhere. Okay, and here in main, let's make a tree. A tree equals a new tree. Now, what data type should we use? Let's use integer. Wow. So a tree of integers equals a new tree of integers. Integer. Now, import from the collections package. Be careful. There is a tree package that you can import from a weird place though. sun.reflect.generics.tree. That's even beyond java.utility. That's a different spot. But anyways, we're going to create a tree and then tree.inserts. I don't know. Let's insert 50. And then we'll insert two more. Inserts 30 and 90. So think about what that's going to do. It's going to insert the first node 50, and then a 30, which is less than 50, and then a 90, which is greater than 50. That's what the tree should look like if our code operates properly. Okay? And then let's say I did it one more time with a 40. So we'll insert those 4 nodes and a 40. Now, we did this before. You guys kind of got this. The way 40 goes is it goes It's less than 50, but greater than 30. So 40 should go right here. 40 should be off of the left, pardon me, the right side of the left node of the root. Woo! Woo! Okay. Let's see how this goes, starting with this, well, starting with the constructor. The constructor of our tree class just basically says, okay, just set this thing called root to null. Okay, I gotcha. So right here on that line, it just makes something called root. It's a reference to what will be a tree node, but right now it's just set to null. There's no tree node there. But then we call the insert method of the tree class. Okay, so let's take a look at what that looks like. Come on, there we go. So according to the insert method, it says, well, if the root is null, oh, root is null, then the root now points to a brand new tree node. Okay, and it takes the data with it. So it's taking that 50 with it. So now we go to the tree node class, and we look for the constructor that matches this. Okay, well, I need a constructor with just data. Okay, so here it is. So the 50 gets passed right here into data. So there's the 50. It then takes that data along with it up to here. And it says this dot data equals data. So the 50 is assigned, and left and right are both set to nulls. Okay. So that seems simple enough. So back here, the root now has a 50 in it. That's the root. And this is null, and this is null. No problem. Now it calls insert on 30. So we go back to the tree class. We go back to insert if root is null. Root is not null anymore. So it drops here. It says root.insert. So now it's calling the insert method of the tree node class. So I better take a look at what that says. So according to the insert method of the tree node class, I've now been passed a 30 right here. And it says, if the data, 30, compares to this data, 50, is less than 0. Well, it is. 30 is less than 50. Then it says, if this, that's the root, dot left is null, oh, it is null. Perfect. Then the left equals a brand new tree node with the data, 30 in it, and according to its constructor, these two will be set to null. Done. It's done here, it's done the insert there, goes back to tree, it's done the insert there, goes back to the main class. And now we call insert 90. Now I'm not going to go through the code for you, but it would then create that, because it would eventually get to the same spot. It would get all the way over to the tree node class, and it would get down to here, and it would compare, and it would be greater, and the right would be null. But now it would call the 40, okay? So 40 is now being passed into first the tree class. So the tree class gets a 40 right here. The root's not null, so it's calling a 40 off this root. Right, so now the insert method is here with a 40 in it, not a 30 anymore. Okay? So it compares 40 to 50. Well, 40 is less than 50. So now it drops down to here. If the left is null, it's not null. The left of 50 is not a null. So it now drops to this else statement. If this dot, so what it does is it now calls this dot left dot insert. So it's calling an insert now off of the left of the root. Well, this is the left of the root. And it's calling insert off of this. So now insert is called recursively with the 40, and it compares 40 to 30. So it drops down to here, it's greater, and the right of that is null, so that's where it builds it right there. And it puts the 40 there. So it's using recursion to the advantage of the tree structure to really be efficient in the way it works. Okay? I hope that explanation made sense. So that's insert. Sweet. Okay? But now, what the heck are we going to do with this tree? We can put stuff in it, but for example, how do we turn the tree into a string? Public string to string. What do I return here? How do I turn the entire tree into a string? How do I output a tree? Any ideas? Look, let me build up a little tree here for you guys. Actually, hang on, maybe I have one. Let's see. We have some ones that we were working on. Previous class. There's this one, I think. Yeah, this is a good one right here. Here's a good tree. This is a nice binary tree. If I told you to print this for me, what order would the numbers come out? Like, how would you do that? Would it start at 82? Would it start down here? I mean, you know that this is the order that you got them, but let's say you didn't know that. Say it came in a random thing. How would you output this? The answer to that question is not as simple as you think. There are several different ways we could output it. Okay? We could output it, for example, by level. Right? There are 4 levels to this, right? So maybe the outputs would go 82. Then for the next level, for this level, there's 2 nodes. So do I go this one, then this one? Maybe 7, 104. But there's nothing saying it couldn't go the other way. It couldn't go 104, 7. For this one, there's 2, but there could be as many as 4 on that row. There could be even more on this row. So is that the way I output it? Or do I start at the bottom and work my way up? So there's several different ways you can output a tree. So I'm going to present some of them to you. The 3 classic ways we go through a tree, and by the way, I'm not going to use the word go through. I'm going to use the word traverse because it's more commonly used. To traverse just means to travel or to walk across. And I'm going to present 3 of them, 3 tree traversals. The in-order traversal, the pre-order traversal, and the post-order traversal. And I'll leave you today with this question. Where have you seen those 3 words before? Anywhere? Infix, prefix, and postfix. That's right. In a lot of ways, they relate to that. It was one of the reasons why I brought it up as well. I knew it was going to come back in trees. So tomorrow, we'll take a look at those. And guess what? The code is short, very short code, but it's recursive. So it's kind of tricky. But we will look at that tomorrow. Have a good day, everybody. Grade 12. So here's where we left off yesterday. Yesterday, we wrote a class called the tree class. The tree class uses our tree node class, and based on a root, an initial tree node, it will then be able to construct a tree. So the constructor is available to us, which just sets root to null. And we are able to insert data into our tree. And the way we do that is, if the root is null, then we just create a new tree node that holds the data. But if the root is not null, it uses a recursive insert method to insert data off of the root. So we looked at how that worked yesterday, and I hope that's clear. But where we left off yesterday was, how are we going to be able to go through a tree? Or the proper word I was going to say was traverse, to travel through a tree. Okay? So in the past, the way I've done this is when we go through the tree, I just output, I do like a system out, and I output the node value as we're each spot. But I think we can go a little bit better this year. So I'm going to suggest that to our tree class, we're going to add another property, a private linked list, because we already have that, of data type T, just called the list, okay? So we're going to have a list here that will be able to keep track of data if we need to. So so it'll allow us to turn our linked lists, or pardon me, turn our tree into a list if necessary. So it'll allow it to become linear, because it's not. So we're going to have to add that to our constructor. List equals a new linked list of data type T. Okay? Oops, extra bracket there. So that's now added to our constructor. That when we build a tree, we'll also build a linked list. Now, as you can see, the linked list won't take up any memory. That's one of the beauties of the linked list until we need it, right? So it's not like an array where it's taking up memory unnecessarily. The beauty of the linked list that we've been building is it uses memory wisely, okay? Okay. Now, this will all factor into our toString method as well, which we'll get to. But before we write a traversal, what if we could search our tree? Okay? We did that with linked lists. But with trees, searching is different, right? Like let me show you a quick tree. Like what if I went 50, 40, 30, 45, 70, 60. Okay, so there's a tree. So imagine I was searching for 42, right? Or imagine I was searching for 40. What's the answer that comes back from that search? Like in a linked list, it was easy. We could say, well, it's at spot 5. But we're not really, this is not a linear structure, so we don't really need to keep track of sort of where it is. So the simplest search we could apply is true or false. Is 40 in the list? Yes or no? Is 42 in the list? Yes or no? So let's do that. Let's make a simple search that just returns a Boolean. Okay? So let's start with that before we do the traversal. Public Boolean search for T data. Okay? This is not a lot of code because we're going to do it recursively. So we're going to return a recursive search for the data. Okay? Which means we're going to be creating a little private method called recursive search. What's that called? Who remembers? What's that called? It would be, the method would date Kim Kardashian. It's a wrapper method, that's right. It's a wrapper method, right? So it's a private Boolean, okay? But before I write it, I'm going to add a second parameter. We're going to search for the data starting at the root. So that's the key there, is the root is the second parameter, which is what we're hiding. We're hiding that from the outside. That's why we just search for the data. But inside, we're hiding the fact that we're starting at the root. So this is recursive search for T data and tree node. And I'm just not going to call it root, but current. So based on the current tree node, let's do a search. Okay? Okay, like I said, there's a lot of code here. But let's see how it works. Basically, if current equals null, what that means is I've reached an endpoint on my tree. So if I've reached an endpoint, I return false. There is no data of this type in this tree. If my current, so for example, if it was an empty tree, root would be null, right? And if current is null, it's not in there. This is an empty tree. So if current's null, return false. Else, if current, or pardon me, I take data, that's the parameter, dot compare to. Compare to is enforced because we use the comparable interface. We cast it as type T. We have to do that. Current dot data. Okay? And if that's less than 0, so that's a nasty line. but that's what it is. We compare the data to currents data. We have to perform a cast there because it doesn't know, that's just casting. And if it's less than 0, what that's basically saying is if it's less than this, then I return recursive search for the data and current dot left. This is a recursive call. So if it's less than, then go ahead and search the left subtree from this point forward. Search the left subtree. And then what I have for the next part is another else if. And if I use a greater than 0, I search the right subtree. And then finally I have an else. Let me just break this all into there. Can you guess what the else is? That's right, return true. The only other option is, there it is. Because if it's not less than the data, and it's not greater than the data, then it must be equal to the data. And if it's equal to the data, I return true. So if it's a null, it's not there. Otherwise, go ahead and search the left side, or go ahead and search the right side. And if it's not less than or greater than, then it must be equal to, and I return true. That's how I perform the recursive search. Simple code, but you have to understand recursion. Okay? You also kind of have to understand that this is not a linear structure, that this is a left-right structure in the binary tree. Now, we can kind of put this to the test, kind of. Even though we can't see the tree at this point, even though there's no way to output all these nodes, I can search. I can do a system out, and I can do tree.search for 30. Okay? It should return true. 30 should be in this tree because I inserted a 30. So let's see if my code works. True. So that's good. Okay? Let me test one of my other ones that's in the tree. Let me test 40. It was the last one I inserted. True. 40's in the tree. What about 50, the first node I inserted? True. Now let's try one that isn't in the tree. 100. False. Good. It works. And as a matter of fact, it is incredibly efficient search. You may not realize what's going on here, but what this search is the binary search. Okay? Now we haven't done the searching and sorting unit yet, but the binary search is the most efficient search there is. The only way that it works is because we're in a binary tree. Because we inserted the nodes already in order. So the nodes are already inserted in order, and that's as a result, this search is incredibly efficient. Okay? Way more efficient than a linked list. Way more. Okay? Like significantly more efficient. All right? So we now have the insert. We can insert nodes. We have a search method. What's left is the way to travel the tree. Okay? The way we're going to travel the tree. And the way it's going to work is it's going to be part of our toString method. Here's the way the toString method is going to work. We're going to take our list. Okay? And if it's already got something in it, we're going to rebuild it by making a new linked list. So we'll just make sure it's a new linked list first, just in case we're calling toString for the second time. Okay? And then we'll create a string called output. Okay? And we'll put tree traversals on there. Okay? And then a new line. At the end of this, we'll return output. Okay? But what we're going to do is we're going to fill up our list, essentially. Okay? And we'll say list equals, and we'll get the list from what's called the pre-order traversal, not pre-order traversal. So what's going to happen is this method that we haven't written yet will return a list of values. Okay? We will then take that list and attach it to output. Okay, so output equals output, or plus equals the list.toString. We'll turn the linked list into a string and attach it to that. But we'll attach something else to it first. So before that, we'll also add that this is the pre-order. Okay, like that. And then we'll turn the list into a string. There are 3 traversals we're going to be looking at. One is the pre-order, so maybe we can even number them like this. 1, the pre-order. Okay. And then we're going to do this 2 more times. So after this, we'll do it again and again for post order and in order. Okay? So we will pick up on this tomorrow. Okay, guys, so let's take a look at where we're at here with the tree stuff. Okay? So we're now at this point, we've got this really good looking tree that uses our tree node, and we've set up a linked list that's ready to hold on to node values should we need it, okay? And we will need it, obviously. So we came down to this toString method that we are going to rely on 3 methods. So yesterday I suggested that why not reorganize this code a little bit so that it's just sort of optimized this way, that we create a string that says tree traversals, and then we're going to add to that string the pre-order, post-order, and in-order traversal. We'll make a call to those things. Those things will return a linked list, and then that linked list will be turned into a string. So here, for example, let's write what one of them will look like. It'll be public linked list called pre-order. Okay? Not per order. That's a typo. Okay? And obviously, it's going to return our list. That's our global object, is the list object. But we got to do more than that. That's not enough, obviously. We're going to fill that list first with all the nodes in the pre-order traversal. So I'm going to explain what that is in a second. Before we do that, we're going to essentially clear the list by making it a new linked list. Come on, computer, catch up. There we go. Okay, of generic type T. Okay, so we will instantiate the list. That will be useful in case it already had something in it. So that will essentially rebuild the list, then we'll fill it up, and then we'll return it. Okay? The filling will take place through a recursive method. So we're essentially, again, using pre-order as a wrapper method to hide the fact that we're going to be doing something recursively here. Okay? And you can go ahead and copy and paste this, because this is going to happen for pre-order, post-order, and in-order. All 3 of these methods will do the same thing. Pre, post, and in-order. All 3 of those methods will instantiate the linked list, do something, and then return it. Okay? Now, the linked list is a global object, so we don't have to pass it back and forth from method to method. It's unnecessarily passed. But what we are going to do, so for example, in the pre-order method here, is we're going to call pre-order, okay, and this is going to be recursive, so we'll call it pre-order recursive, okay? And what we pass it is our root node, okay? So this will be a method that we're going to write, the pre-order recursive, starting at the root. You will then do this with post-order recursive, and down here within order recursive. So those will be 3 helper methods that we will put in that will be recursive, that will help these 3 methods, these 3 wrapper methods, do their job. Okay? And they will be private methods. They will be hidden within the class. These are the public methods that give you all the nodes in post order based on returning it as a linked list. Okay, so you can go ahead and create these 3 methods. You can use the light bulb if you want, or you can just manually key them in, whatever you feel is useful. They'll be void methods. They won't return anything. Okay? And here they are. Whoops. The only thing I would suggest about these 3 recursive methods is let's not call it root as a parameter. I know that's the one we passed it, but let's just call it current. It's just a current node. It's a current node that we're going to be looking at recursively. Now, here's the good news. What the code we're going to put in here is really short. It's like 4 lines for each of these. But the concept of what's going, like any recursive method, they're short methods. But like with any recursive method, it has a little bit deep of an understanding of what's going on there. So I've made a little animation to try and demonstrate what's going on here. All right? So let's take a look at trees in this context. Okay. There we go. To travel a tree, or to traverse a tree, means to visit every node. And that's what we're trying to do here. We're trying to visit every node. The traversal algorithms are essentially the same whether the tree is in order or not. Our tree happens to be in order, right? The way we designed it as a binary tree is when we insert a node, it gets inserted into its correct spot. But if we just randomly inserted the nodes, and we didn't worry about that, the traversal would also be the same, okay? Now, the reason you'd travel a tree would be printing the nodes, counting the nodes, searching the nodes, etc. We happen to be using it right now for printing purposes, for turning it into a string. But the 3 traversals, pre-order, in-order, and post-order, are very similar to what we studied in stacks and queues about those different forms of equations, okay? But this is a recursive process. Okay, so here's the animation. When going in pre-order, the way it works is you start by visiting the current node. By visiting, the way you could describe that is that's when it gets outputted. Or, for our case, that's when it gets put into our linked list. So the first thing we do is, based on the node we're at, put it in the list, or output it. Then travel the subtree to the left. When you're finished traveling the subtree to the left, travel the subtree to the right. So the way this would output would be, because where do we start? We start at the root. So I would output the roots, then I would go to the left subtree. Now this is recursive, so the algorithm starts over again. So I start off at 1 again. I output the node. And then I go to the left subtree. I output the node. Now from 10, what's the left subtree? Null, right. So I wouldn't need to output the null. What would be my next instruction? Go to the right. What's the right subtree from 10? Null, so I don't need to output that. So then this would be, 1, 2, 3 would be done recursively at this level. Now I'm back here at this one. The next instruction, I just finished 1 and 2, I finished going the left subtree. Now I go to the right subtree. So the next node that would be outputted would be 40. Then 40 goes to the left subtree, and then it goes to the right subtree. And then this is done recursively. This one's done recursively. Now I'm back at the root. I've done the whole left subtree. Now I do the whole right subtree. So in a pre-order traversal, the nodes would be outputted in that order: 60, 20, 10, 40, 30, 50, 70. Okay, I'm just going to skip the code because we're going to key in the code in a second. In a post-order traversal, it's the same 3 instructions, but in a different order. Now I visit the left, then I visit the right, and then I output the node. So starting at the root, first thing I got to do, go to the left. When I'm at the 20, go to the left. When I'm at the 10, Go to the left. Oh, that's a null. So instruction 1 is done. Go to the right. Oh, that's a null. Instruction 2 is done. Instruction 3, output the 10. But then that's done recursively. Now I'm back here at the 20. I've now gone to the left, so now I go to the right. And the recursion starts over again. So the output of the nodes in this case will be in this order. So that's weird. That's what the post-order traversal will output. 10, 30, 50, 40, 20, 70, 60. Okay? Notice how that kind of does that output. 10, 30, 50, 40, 20, 70, 60. Whoops. So that's the post-order traversal. It's the same 3 instructions, but in a different order. And guess what? The in-order traversal is the exact same 3 instructions in the final different order. So go to the left, then visit, then go to the right. Watch how this one works. So from the root, I go as left as I possibly can to 10. Output it. Then, from the 20, because I'm back at the 20, go as left, pardon me, now I've gone from the 20 as left as I can, visit the current node at 20, now go as right as I possibly can, but when I get right here, I got to go left again. Then I got to go to 40, then I got to go right again. Then I got to go back to 60, then I got to go right again. Notice something about the in-order traversal, the way it outputted the nodes. Does anyone notice anything about them? They're literally in order, okay? So that's the way it essentially works, okay? So let's key this in. I know it's a little bit tricky to grasp right now, so let's try this, okay? Let's try and get this done. Yeah. Okay, so we'll start with the pre-order traversal. So first of all, we have to deal with leaf nodes. If current, whoa, that is all capital letters. If current equals null, okay? So if current is null, I've reached a leaf node. So that's when the recursion should stop. That's a base case. So I'll return right here, because it's a void method. So this is a base case. That's what stops the recursion, right? Is when I've reached a tree or a leaf node. I'm done. The recursion should stop at that point. Okay? Now, according to pre-order, what I now need to do is I need to add the current node to my linked list. Now, we have various ways to add a node to a linked list. But I'm going to actually make a suggestion right now. Could you guys just take a second to open your linked list class? This will only take a second. So go to your linked list class. And let's add a simple method to this thing. Let's add a simple add method. So public void add t data. Let's just be, when you add to a linked list, what would be the instinctive way it would be added? To the back, would you say? Just always add it to the back? So let's call insert tail data. Let's just call that. Now we could have called that back in the tree class, but I like just keeping it simple sometimes. So let's just use that, and let's just use this new add method to add current, okay, dot data to our linked list. And we have to make one quick cast as data type T. Okay, did I go too quickly there? Okay, so let me just recap. In the linked list class, we're using this add method right here to add using insert tail. And then I'm just making it simpler on me here so that I'm just adding the current data to the linked list. Okay, that's what I'm doing. So if current is null, return. Otherwise, add it to the linked list, and now comes my recursion. Now I do a pre-order recursive call to current dot left, and then I do a pre-order recursive call to current dot right. Okay? That's what it does. It visits the node, and then it visits the left subtree, and then it visits the right subtree. And that's it. 4 lines of code to do a pre-order recursive. Okay? Got an error, Mika? Actually, since we're here, I'm going to suggest we add one other little constructor to our linked list class. So if you wouldn't mind, just jump over to your linked list class for a second. This will just take a second. Let's make a third constructor, public linked list. You'll kind of see why later. From a linked list. Make a linked list from a linked list. Okay? There's a good reason for writing this code. We'll get to it later. So what we're going to do here is, when past a linked list, turn the current linked list into the same thing. It's like a clone kind of a thing. So this dot destroy will destroy the current linked list. And then we'll just loop through linked list dot length. Back up there a bit. And we'll say this dot add linked list dot get spot I. And we have to make one little cast to data type T. Okay. So this is what I'm proposing, is just this little constructor here. Just add this little constructor right there. My little drawing software is not working well. So add that constructor. It's going to come in handy, trust me. Okay? Trust walks. So a third constructor. So we have the default constructor. You could just make a blank linked list. We have a constructor that allows us to build a linked list from an array. And then this one, which builds a linked list from another linked list. The reason why this one will become useful is because we use the linked list for inheritance. That's why, but we'll get to that in a little bit. It's going to be cool. Okay, anyone not got that? Back to the tree class. So now, here's how easy this is now going to be. These 4 lines of code are going to be the exact same 4 lines in the next 2 methods as well, but in a slightly different order. But however, it's important that you don't make this mistake, because you might want to just try copy and paste. But when we copy and paste, we're going to have to change the name of this, not as pre-order traversal, but to the other ones. So I'm going to actually suggest not copying and pasting here, because otherwise, well, actually what I'm going to suggest is copy the first 2 lines. Go ahead and copy the first 2. Okay? But the other 2 I'm going to suggest we actually key in, because a copy paste might actually mess it up. Okay, so with post order recursive, not pre-order, but post, we put the adding of the node as last. What goes before it is a post order recursive call to current.left, and then a post order recursive call to current.right. Oops. Okay? So that's how post order recursive works. You still have the base case first, then you visit the left subtree, you visit the right subtree, and then you add the node. Notice how that's slightly different than the one above it. In the one above it, this will always be first. I visit the node, then I go left, right. Now, this is actually super easy to remember. If you think about the wording itself, pre and post. Step out of computer science for a second. What does the word pre mean? Before. What does the word post mean? After. Where is this line being put amongst the 3 instructions? It's being put first, or it's being put before. Where is that line being put in the post order traversal? It's being put after. And notice these always just go left, right, like you would imagine they would go, like you're taught to read in North America. You're taught to read from the left to the right. So guess where it goes in order traversal? What would the word in mean? What's another version of the word in? In between, exactly. So it's actually fairly easy to remember in that one too. So in order recursive, we first go to in order recursive to the current dot left, then we visit, then we go to the in order recursive to current dot right. Okay, so here you can see with in order, the part where we add it is in between left and right. Okay? Now you still might be difficult to grasp how this works in terms of a tree. But the actual code lines are fairly simple because of the recursion taking place. Recursive algorithms are always going to be simple in their design. But this now, theoretically, should work. We now have everything in place to execute our toString method. It will output them in post, pre, and in order. If now we take a look at our main, if we go to main, we now have a tree built of integers. We executed a search, but let's do something better than the search. We knew the search worked. Let's just output the tree at this point. So we can actually output, because we now have the ability to turn the tree into a string, we can output the tree. So let's try this. Let's run this code and see what happens. Why, look at that. We have some output happening. So here's what it's saying. So let me take a second to try and draw this. Okay? So the way our tree was constructed, according to the instructions we gave it, was it started with 50. That'll be our roots. Then it inserted a 30, and the 30 is less than 50, so it went there. Then it inserted a 90. The 90 is greater than 50, so it should have inserted it there. Then it inserts a 40. The 40 is less than 50, but greater than 30, so the 40 should have gone there. So that's what our tree should look like. So let's see what the ordered traversals does with this. According to the first traversal, it says, output this in pre-order. So pre-order means, 1, output the current node. We're always going to start at the root. It's the only place to start. So you start at the root, output 50. It did. Then go to the left, and the algorithm starts over again. So the algorithm says, output the current node, 30. Then it says, go to the left. When left is null, it just returns. Then it says, go to the right. The algorithm starts over again. Output the current node. Then go to the left, null. Go to the right, null. Just like here was null. So it's done left, it's done right. That recursion is complete. Now it's gone back to this one. It's gone all the way to the left. It's gone all the way to the right. This recursion is complete. Now it goes back to the original recursion. It's gone all through the left. Now it'll go to the right, goes to the left, goes to the right, outputs the node. So you can see how the pre-order traversal works on that round. Okay? Now, let me backtrack. Can't I undo? Come on, let me undo. Oops. I got to clear it. Silly, silly software. All right. Okay, so now I think it's worth it for me to still draw out this tree. 50, 30, 90, 40. Okay, so let me run the post-order traversal. In post-order, the way it works, post means last. So starting at the root, it goes to the left, restarts the algorithm, goes to the left, it's a null, so it's done. Then it goes to the right, restarts the algorithm, goes to the left, goes to the right, and once it's gone as far left and as far right as it can, it outputs the node, 40. At this point, this recursion is done. Now it goes back to the previous recursion. It's gone to the left as far as it can, it's gone to the right as far as it can, so the next instruction, output this node. That recursion's done. Now I'm back here. I've gone left as far as I can. Now I go right. Recursion restarts. Go to the left, go to the right. I'm done this little recursion. This guy's done. Output that node. Finally, I'm back here at the original recursion. I've gone left as far as I can. I've gone right as far as I can. Output this node. And notice how our post order is working there as well. Okay? So, cool. It seems to be working. Okay? Finally, I still think it's a useful exercise. Redraw the tree. How does it work with in order? Okay, here's how it goes with in order. With in order, the output is in between. So we're starting at the root, go to the left, restart the recursion, go to the left. Okay? I can't go left anymore. The next instruction in between is output the node. So at this point, it outputs this node 30. But now it goes to the right. It restarts the recursion. Go to the left, output the node, go to the right. Right's a null. This recursion is now complete. Now it's here. It's gone to the left, it's outputted the node, and it's gone to the right. This recursion is now complete. So now I'm back here at the original one. It's gone to the left as far as it can. The next instruction in between is to output this node. And now it goes to the right. Restarts the algorithm. Go to the left, output the node, and then go to the right. And we're done. That's how the three traversals work. Okay? Yes, by the way, if you were thinking, I wonder if these pre-order, post-order, and in-order are related to that stuff we did with the whole math thing, with the equations. Do you guys remember those ones? We talked about it yesterday. Nick, was it you that pointed that out? That there was that you saw pre, post, and in what? Prefix, postfix, and infix. That's right. Absolutely. That's how they evaluate those. They put them in trees and then run the traversals, and it works. Okay? All right. So that's pretty cool that we've got these trees that can do this. Okay? And I think, for the most part, that's all I wanted to do with trees with you guys, was this concept. Okay, I have a little bit of an animation just to wrap up today, and a little bit of theory as well on this, just a little bit. Okay, so hang on one sec. Okay, so with an unordered tree, that's not what we built, by the way. We built an ordered tree. Mika, I see your head. Let me just finish this, then I promise I'll come give you a hand. Okay? With an unordered tree, you can put values anywhere. But an unordered tree is not that useful to you. Okay? With an ordered tree, there's only one spot you can put a node. And that's what we built. We built an ordered tree. So here you can see, if we do 15, 8, 12, 19, 5, 23, it would do it in that way. 15, 8 is less than 15, 12 is less than 15 but greater than 8, 19 is greater than 15, 5 is less than 15 and less than 8, and 23 is greater than 15 and greater than 19. Okay? That's the way it builds trees in an ordered tree. If it receives the numbers in a different order, it will build a different looking tree. Sometimes programmers will shorten the binary search tree to just a BST. BST for binary search tree. Okay? By the way, you'll notice why it's called often called a binary search tree, is because it's so efficient at searching. Okay? We wrote that search algorithm. We wrote the insert, we wrote the tree class, so this is all in the notes. Okay? We've already done this. But I just wanted to wrap with a little bit of tree theory. Okay? So there's another traversal that we didn't code called the breadth first traversal, in which you visit the nodes by level. Okay? So for this one, for example, you would, for each level, output the nodes, right? Like that. There is no simple recursive way to do this. This would require a larger algorithm. Okay? To do this one, most likely, I don't know if you can read there, the most common way that this is done is to use a queue object and queue in the nodes as you travel through it. You don't need to know how to do that for, I don't even think you need to know the traversals for IB, to be honest with you, but you will learn these in university, so I'm going to teach them to you because it's better to know this. Okay, but that's a theory of another traversal, is the breadth first traversal. Okay? Now, as well, one thing you don't need to know in IB, which seems like something you should know, but is actually very hard to do, is how to remove nodes from a tree. Now, you might think that that's an easy thing to do, but it's actually not, because there's 3 different scenarios here for removing a node. 1, if the node has no children, that's actually easy. That's just, what kind of a node would have no children? Leaf node, or it's also possible that a root node could have no children if it's just one node tree. Or the node has 1 child. Would that be an easy removal? You could just switch them, right? Couldn't they just be switched and that'd be okay? But if they have 2 children, we have to do what's called a rotation of the tree. Okay? To remove a leaf, you just kill it, right? That's easy. To remove the 1 child, just replace the 2, like basically swap the 2 node values and then delete the other one. Okay? But with 2 children, it's a little more difficult. Okay? So removing the 10, easy. I just set this left pointer or this left reference to null. Okay? In this case, to remove the 2 from this tree, it's pretty easy. All I do is redirect this guy around that one, redirect it, and then like we did with linked lists, and then it's no longer available. So removing 0 children, easy. Removing 1 children, easy. Removing 2 children is much more difficult, because in the middle of a tree, you've got to kind of look at the nodes below you, and you'd actually have to do what's called a rotation of some of the parts. I'm not going to teach that to you. It's a little more challenging, and we kind of don't have time. Like, that would take a couple classes to sort of work the algorithm out of that. But you don't have to know that, okay? That's what we needed to know about trees. Now, before we leave trees, though, let's go with a super cool example. Let's just fluff up our example a little bit, okay? But to do this, I'm going to ask you guys to make a quick modification to your stack class. Hang on one sec. I'm just going to... Okay, here's what I want you guys to do, real quick. Go to your stack class. And in your stack class, let's add a second constructor to the stack class. Public stack. We can build a stack from a linked list. Let's just call it list. Okay? Here's all you need to do. Make a call to the superclass and give it the list, which is, by the way, why we wrote that method. So we're going to build this into the stack class that you can make a stack from a linked list. Okay? Then, go to the queue class. We're going to do the same thing. In the queue class, also make a second constructor. Public queue from a linked list, called list, and same line. Just make a call to the super constructor and give it the list. Okay? Yeah? You guys got that? Anyone need a minute? So both the stack class and the queue class now have those 2 constructors as well. Okay? All right, let's get super cool. Go to main. Let's rewrite our code in main. So let's start with an array. Let's make a string array. String array called array equals, and we'll just do it this way. We'll feed it some stuff. Why don't we feed it, let's be simple. Let's just feed it, I don't know, letters? Or do you guys want to do words? If I do let's do random words. Random word. Jack. That's easier for me to spell. Okay, mayonnaise. Is that right? Okay. Erickson, random word. Okay. Jesse, random word. That's not that random. That was the one you used before. Okay. Hang on, I got to move down the line. Kyle, random word. Mika, random word. What? Oh, XIA, is that right? Okay. Nick, random word. Super. Aiden, random word. What? Spell it. Wow. Okay, good. So we got our random array, sort of. Now, from that array, let's make a linked list, data type string called list equal to a new linked list, data type string. We've got a generic linked list. This should work. I might have to import it, but whoops, I imported the wrong one. Not that one. I want to import my linked list from the collections package. There we go. And since we have the constructor, pass the array to it when we construct it. So this linked list will be constructed from the array, right? Because we have that constructor. Then, let's make a stack of data type string called the stack equal to a new stack, data type string. And let's pass it the list. Because we've built into the stack class the ability to construct the stack from a linked list. So we turn the array into a linked list. We turn the linked list into a stack. Let's make a queue of data type string called the queue equal to a new queue. Data type string. And let's pass it the stack. Because of polymorphism, a stack is a linked list. And because a stack is a linked list, it will call the constructor building it from the linked list. And then finally, we'll make a tree called of data type string called the tree. Let me just space this out a little bit. Oops. It's easier to read. So I'm going to make a tree equal to a new tree, data type string, and I will call the constructor and pass it the queue. Due to polymorphism, a queue is a linked list. Uh-oh, what happened there? Oh, we don't have that constructor yet. Oh, I think we better have it because all I wanted to then do was output the tree. So we have one job left to do, writing a constructor in our tree class that takes a linked list. Because look at this. This is all the weeks of work coming together here. We start with an array. That's grade 11 content. We're past that. We turn the array into a list, a linked list. We turn the linked list into a stack. We turn the stack into a queue. We turn the queue into a tree and output the tree. But for this to work, we need a constructor within our tree class that does this. So let's, anyone not on that? Anyone not got that? So let's jump to our tree class to add that constructor. Public tree takes a linked list called list. Okay? Actually, let's call it so that it's just a little bit easier. Let's call it linked list because I don't want to conflict with that one, which is also called list. Okay? Anyone have an idea how this would get done? How could we do this? Well, we're constructing it, so let's set the root, not the rot, the root to null. Then we just loop through our linked list. So through linked list dot length, and we say this dot insert list dot get spot I, and the only other thing we need is to cast it as data type T. And we've got it. That's the constructor. The constructor just sets the root to null and then loops through the linked list, inserting all the nodes. And remember, that's done recursively, okay, as it goes and gets them from the linked list. Now, if this works, that's some serious bad you-know-what code going on here. Let's see. We're gonna get a crash? Ah! Correct. Linked list dot get. Good call. Holy moly, it outputted a tree. Look at that. It outputted a tree. And look at the in-order traversal. It's in order. Ah. How do you say that? Aiden, how do you say that? Dinosaur, hypoxia, mayonnaise, super tree. Is it ironic that these are the last two words in this example? Because you guys did a super job making this tree. And it's almost time for the bell. What a finish.